In this video, we'll take a look at a confidence interval for a proportion. So what is a confidence interval? So recall the plain M&M simulation from the previous written assignment. The population proportion of orange plain M&Ms produced is 0.20 or 20%. So we know the population proportion produced. I purchased a bag of M&Ms that had 100 candies, and I had 24 orange candies in my bag. So if I didn't know that the population proportion was 20%, I want to use a confidence interval to estimate the population proportion based on my sample. So how would we estimate with a sample if we didn't know what the population was up front? So the example we're going to look at is we're going to construct a 95% confidence interval to estimate the proportion of orange M&Ms produced based on my one sample bag that had 24 orange out of 100 candies. So the first estimate we can use is a point estimate. The point estimate is just the actual p-hat proportion that you had in your bag. So p-hat is 0.24. Now we're going to construct a 95% confidence interval to estimate the proportion of orange M&Ms. So what we're going to do is visit notes and take a look. This is in your posted in Canvas or in the textbook. What is a confidence interval? So a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. And we denote it 1 minus alpha times 100%. So here's what that means, okay? So we're going to look at a 95% confidence interval. So I'm going to have my 95 or my 0.24 in the middle, and then I'm going to find a estimate, a margin of error, and count to the right and to the left of my proportion to figure out what my guess is based on my sample of size 100. So we want to look at, before we do too much here, what does 95% confidence interval mean? Okay, so a 95% confidence interval means that the inside is of the standard normal. We're shading 95% in the middle, or 0.95. And a critical value is 1.96. That means we need to go 1.96 in each direction to do that. And I'll do that on the distribution in a minute. Then what we need is we need to know how to estimate. Here's our constructing it for a population proportion. What we need is p-hat, and then we need some sort of an estimate of the standard deviation. We don't have the population proportion, we have p-hat instead. So we're going to estimate the standard deviation as the sample that we have, p-hat. So let me go back to the example. So what in the world did that just mean? So here's what I'm going to do. We take our p-hat of 0.24, and then I'm going to estimate a standard deviation, or it's really a standard error, by using that value. 0.24 times 1 minus 0.24 divided by the sample size n. So I'm estimating, it's a sample error, not a standard deviation. I'm estimating based on my sample. And what I want to do is, I have 0.24 in the middle. A 95% confidence interval means I want an area of 0.95 on either side. On the standard normal distribution for 95%, the z-score that goes with 95% to the right and to the left is positive and a negative 1.96. If you don't remember how that happens, we have 0.025 area on either side to have 95 in the middle, and you use inverse normal. .025 mean standard deviation. Let's see. Oh, 0, 1. Okay. So if we go 1.96 standard deviations to the left and to the right, that's going to give me an area of 0.95, and that's going to be my interval that my guess is of the population proportion of M&Ms. So there's a formula that says you take p hat, your point estimate, add and subtract your critical z. These values, 1.96, are considered your critical z's. You're going 1.96 standard deviations on either end. So that would be p hat plus or minus critical z times your standard deviation, which was the p hat times 1 minus p hat over n. So to calculate by hand, let me erase this and give myself a little bit more room. To calculate by hand the confidence interval, we take the 0.24 and we're going to plus or minus 1.96 standard errors on either side times my square root of p hat times 1 minus p hat over n. So p hat in my case is 0.24 and n is 100. So we substitute the 0.24 and substitute 100 for n. Okay, this is called the margin of error. So if we put that on the calculator, in the calculator, I get 1.96 times the square root of 0.24 times 1 minus 0.24, which is 0.76, divided by my sample size of 100, and I get 0.0837. So I'm going to take 0.24 plus or minus 0.0837. So I'm going 1.96 standard deviations to the right and to the left. So I get 0.24 minus 0.0837. That's my lower value, 0.1563. My upper value is what we get when we take 0.24 plus 0.0837. So I'll repeat the last line, go over and make that a plus. I end up with 0.3237. So 0.1563, 0.3237. So what does that mean? That means based on my bag of 24, or out of 100, I'm estimating what I think the true population is. How do I do that? I construct a standard error. 95% confidence means I'm going to go 1.96 standard deviations either way, and I end up with this interval. So my interpretation is I am 95% confident that the proportion of orange M&Ms is between 0.1563 and 0.3237. Okay, so the estimate, a confidence interval, is an estimate of a population parameter, in this case the proportion of orange, using an interval. So if I used a lower value, 95%, if I used 90%, then my interval would be narrower. If I used a higher level of confidence, my interval would be wider. So that's the reasoning behind a confidence interval and how you calculate it by hand. We can calculate it on the calculator. So we are going to use, this one is a proportion. This is a 1 proportion Z interval. So on the calculator, let me bring it up. We're going to hit stat. Let me clear it out. Stat over to tests. This is a 1 prop z interval. We want to know x, how many M&Ms. We want to know n out of a bag of 100. Our confidence level is 0.95. Calculate, and notice we get the same thing using technology that we did up above. Okay. All right, so if we're going to do StatCrunch instead, okay, so I'm going to get to StatCrunch. We go to our class, hit MyLab and Mastering, open, select StatCrunch, go to the StatCrunch website, and this is stat. These are proportion statistics. We have one sample with summary. That means my number of successes. I had 24 orange out of 100. We're going to perform, it allows you to do hypothesis test and confidence interval. So one at a time. We're doing a confidence interval of 0.95. Method, just leave it default. Hit compute. And notice I get the lower limit of 0.1562, upper limit of 0.3237. We get the same thing whether we're using StatCrunch or whether we're using the calculator. And we've got the screenshots here. So again, I've got the interpretation. I'm 95% confident that proportion of orange M&Ms produced is somewhere between 15.6% and 32.4%. So what does that 95% confidence mean, or any level of confidence? So if we were to continue taking hundreds of samples of size 100 and constructing a 95% interval for each sample bag, our intervals would capture the population proportion 95% of the time. So I'm going to show you results from a simulation from StatCrunch. This, I could choose sample size of 100, and I did 100 intervals with a confidence level of 0.95 with a population proportion of 0.2. So this represents taking 100 different bags of M&Ms. So this first one, this is the proportion of M&Ms, is the middle is this green dot. And then the green line for each one is the interval. So notice with each, not every single one of the 100 bags of M&Ms, not all the confidence intervals contained the true proportion. In this simulation, we were left with 1, 2, 3, 4, 5, 6 that didn't. So 94 contained it, 6 didn't. So 95% confidence means if we kept running the samples over and over again and computing confidence intervals for each individual sample, 95% of the time, it would be in the interval. So it's not a probability concerning anything other than how many times your sample is going to have the actual value of the population in it.